Okay, so we're on lesson 8 of our statistics unit, variability in a distribution. Our I can statement is I can compare and contrast two small data sets that have the same mean but different amounts of variability. So I want you to look, this is our focus. What happens when we have two data sets that have the same mean but yet they have different variability? What is that going to look like and what will that mean for us? So here's our first problem. Let's listen to it.
Marvin's family is planning to move to either New York City or San Francisco. Marvin has a cousin in San Francisco and asked her how she likes living in a climate as warm as San Francisco. She replied that it doesn't get very warm in San Francisco. Marvin was surprised, and since the temperature was one of the criteria he was going to use to form his opinion about where to move, he decided to investigate the temperature distributions for New York City and San Francisco. The table below gives average temperatures in degree Fahrenheit for each month for the two cities.
Alright, so let's look at our data that Marvin has collected. How would you describe the temperatures in New York City? Well, notice that we start at 39, we go up, 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 and then back down. So how would I describe that? Well, it looks like the temperatures change a lot throughout the year. Temperatures start low, they get higher, up to 85, and then they go back down to being low. How do you describe the temperatures in San Francisco? Well, I start at 57, I go up, up, and down. Notice how I'm only going from 57, though, up to 70. Well, here in New York, I went from 39 to 85. That's a big difference. So what do I notice? I notice that the temperatures do not change as much throughout the year. Okay, so let's look at this. Calculate the annual mean monthly temperature for each city. You can use a calculator. So what am I going to do? Well, I'm going to add up all these numbers, 39 plus 42 plus 50. So let's check. 39 plus 42 plus 50 plus 61 plus 71 plus 81 plus 85 plus 84 plus 76 plus 65 plus 55 plus 47. So my total is 756, and now I need to divide that by, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, since there's 12 months. So I'm going to use my calculator again. Divided by 12 equals 63. And then I'll do that same process where I'm adding up all these numbers for San Francisco. So 57 plus 60 plus 62 plus 63 plus 64 plus 67 plus 67 plus 68 plus 70 plus 69 plus 63 plus 58. Now I'll get 768. And there's 12 months again. That hasn't changed, so I divide it by 12. Now I'll get 64. So now let's check. And look, our means match. And they match what we had for our answer. So recall from our problem that Marvin is trying to decide on which city he wants to move to. What is your advice to him based on comparing the overall annual mean monthly temperatures? So all I'm doing is, for this one, comparing the overall mean monthly temperatures. No other advice, not the more exciting, the funner city, just based on that temperature. Well, based on the mean temperature, since they're almost the same, it looks like Marvin can move to either city. That's all he's worrying about. He can move to either city and not have to worry. Okay, let's listen to this part.
In the previous example, you found the overall mean monthly temperatures in both the New York City distribution and the San Francisco distribution to be about the same. That didn't help Marvin very much making a decision about the two cities. Since the mean monthly temperatures are about the same, should Robert just toss a coin to make his decision? Is there anything else Robert could look at in comparing the two distributions?
So what do you think? Should Marvin just toss a coin? Well, probably not. That's not a very mathematical nor smart way to make any life-changing decisions. So what else do you think Martin could use to make a decision? Well, look at our means, and look at our data, and look at how spread out they are. He should consider the range of the variety of temperatures in each city. New York can get really cold, 39, up to kind of hot, 85. San Francisco, though, is a much smaller range for temperatures. It only gets from 56 to 70. This could be good in case he doesn't want to buy as many clothes, since he doesn't need winter clothes in San Francisco. It could be good if he doesn't like the cold weather, so he might want to look at San Francisco. Or maybe Marvin likes this cold weather, so he does want this wider range. But he should consider that portion. Okay, listen to this question.
Variability was introduced in an earlier lesson. Variability is used in statistics to describe how spread out the data in a distribution are from some focal point in a distribution, such as the mean or mode. Maybe Robert should look at how spread out the New York City monthly temperature data are from its mean, and how spread out the San Francisco monthly temperature data are from its mean. To compare the variability of monthly temperatures between the two cities, it may be helpful to look at dot plots. The dot plots for the monthly temperature distributions for New York City and San Francisco City are above.
So, how are these two dot plots different? Well, we already discussed it briefly, but they're different because this New York data is really spread out. It covers a wide range of temperatures. However, the San Francisco data is really clustered together. It doesn't cover as wide of a range as temperatures. Look at all this extra temperature range that New York City has, that San Francisco doesn't. That's a huge amount over here. So maybe Mara wants to take that in consideration too, not just the mean temperature. Okay, mark the location of the mean on each distribution with that balancing symbol. How do their distributions compare based on their means? Well, I remember for New York City, it was 64, and for San Francisco, it was 63. So they should be right here. How do these distributions, though, compare based on their means? Well, it means that their means are about the same. My means were really close to each other, so there's not much difference based on their distributions if I'm looking at just their means. However, we know that's not the case when I'm looking at variability. They just have the same mean almost, but their variability is very different. Okay, describe the variability of the New York City monthly temperatures from the mean of the New York City monthly temperatures. So I'm looking at the monthly temperature compared to that mean temperature. Monthly temperature compared to the mean. What variability do I see? Well, I see that there's a widespread variability. There's a lot of change. The temperatures are widespread around the mean. We have a low of 39 to a high of 85. So my temperatures aren't very close to that mean. Now describe the variability of San Francisco monthly temperatures from the mean of the San Francisco monthly temperatures. So how do the means compare to this monthly temperature in San Francisco? Well, the temperatures are clustered or gathered around that mean. We have a low of 57 to a high of 70. That's really close, all of them, to that 54 or 64 degrees for San Francisco. Okay, now compare the amount of variability in the two distributions. Is the variability about the same or is it different? If different, which monthly temperature distribution has more variability? Explain. Well, remember, just in case we forgot, variability means the amount of what? It's the amount of change in the data, or it's the spread, how spread out it is. So do our distributions look like they have the same amount of change or the same amount of spread? Well, not really. We see that there's a wide spread up here but there's not as much spread down here in the San Francisco. So the variability is different. Now it's asking us which one has more variability, so I'm stating that. The variability in New York City is much greater when compared to San Francisco. Notice how much my data changes in New York City compared to how little it changes in San Francisco. Okay, if Marvin prefers to choose the city where the temperatures vary the least from month to month, which city should he choose? So Marvin wants our temperatures to stay almost the same throughout the whole entire year. Where should he live? Well, he should choose San Francisco because the temperatures vary the least. We go from a low of 57 to a high of 70. New York City has much more variability. We have a low of 39 all the way to 85. So there's a lot of change in temperatures for New York City up here. Okay, let's listen to the statement. Think, is Marvin correct?
The mean is used to describe the typical value for the entire distribution. Trinity asks Marvin which city he thinks has the better climate. He responds that they both have about the same mean, but that mean is a better measure or a more precise measure of a typical monthly temperature for San Francisco than it is for New York City. She's confused and asks him to explain what he means by this statement. Marvin says that the mean of 63 degrees in New York City, 64 degrees in San Francisco, can be interpreted as a typical measurement for any month in the distributions.
So, was Marvin correct? Well, let's listen to this explanation to find out.
What Marvin is saying is that 63 degrees or 64 degrees should represent all the month's temperatures fairly closely. However, the temperatures in New York City in the winter months are in the 40s and the summer months are in the 80s. The mean of 63 isn't too close to those temperatures. Therefore, the mean is not a good indicator of typical monthly temperature. The mean is a much better indicator of the typical monthly temperature in San Francisco because the variability of the temperature there is much smaller.
So Marvin's statement of saying 63 degrees for New York and 64 degrees for San Francisco represents all the data for an average temperature is correct, but it doesn't represent our typical temperature. Our typical means normal or expected. If I have 64 degrees for San Francisco, and I'm saying that's a typical or about a normal temperature for San Francisco, that's pretty close to being correct for all the months. It's not very far off from 57, and 64 is not very far away from 70. However, look at New York City. Since its data is spread out, when I say 63 degrees is a regular expected temperature, that's not really true because 39 is very far away, and 85 is very far away. So we have this. When our data is far away from the mean, most of our data is far away from the mean is not a good indicator for our center of the data. So let's look at this question. When is it a wise idea to use the mean as an indicator of expected or typical values? Well, it's a good idea to use our mean as expected or typical values when they are closely gathered around the mean. If the data is spread out, then the mean is not a good indicator. So here, my data is spread out, so my mean is not a good indicator. Here though, my data is really close around my mean, so that mean is a good indicator for typical or expected values. Alright, consider the following two distributions of times it takes 6 students to get to school in the morning and to go home from school in the afternoon. To visualize the mean and variability, draw data plots for each of the two distributions. So here's my first data plot of 6 students, here's my second. If you had something that looks like that, then you were on the right track. Okay, what is the mean time to get home from school in the morning for these 6 students? And what is the mean time to get from school in the afternoon for these 6 students? So you can use a calculator, which you should get for the morning should be 14, and you should actually get the same answer for the afternoon. So now let's think of this question. For which distribution does the mean give a more precise indicator for a typical or expected value? Which one is the mean a better indicator? Well, I'm going to put my little triangles right at that balancing point. If you're stuck, reread this sentence. When is it a wise idea to use the mean as an indicator of expected values? When the values are closely gathered around the mean. So which one do I have my values closely gathered around the mean? Well, it's this morning one. Notice how my data points are really close to my mean, whereas in the afternoon, look how far spread out my yellow oval is. So the morning mean is a more precise indicator. The spread of the afternoon data is far greater around the mean. Okay, we have one last problem to get through. So consider the following data on the number of green jelly beans and 7 bags of jelly beans from each of 5 different candy manufacturers. All good, best, delight, sweet, yum. The mean in each distribution is 42 green jelly beans. Draw a dot plot of the distributions of the number of green jelly beans for each of the 5 candy makers. So our very first step is drawing this dot plot. You should get something that looks like this for all of them. Yum, good, best, delight, sweet. Please note this information because it is going to be important. The mean is 42 jelly beans in each distribution. So what is the mean of all good? Well, it is 42. What is the mean of delight? It is also 42. So let's go to this page now. Order from most variability to the least. So what I'm going to do is, they're all at 42, so I'm just going to put my little triangle so I remember where they are all at. This is my balancing point. So which one has the most spread? Well, let's look. This yum is spread out from here to here. All good is spread out from here to here. Best is spread out from here to here. Delight and sweet. So which one has the most variability? Well, my most variability is this long line, and it is on best. So that's going to be number 1. My next line that's spread out farthest from my mean is delight. So that is a 2. My next one, all good. Nope, that one's actually really close around the mean. So I'm going to keep going. These two look about the same. So since they're about the same, I'm just going to take an educated guess for 3, 4, and 5. Notice how all good, they're all really close around this 42. So here's my order from the most variability to the least. So let's see how our answers compared, and look. We were really right on. Okay, now our last question is, for which company would the mean be considered a better indicator of a typical value? So which one is my mean the best indicator? Well, again, let's look back here. What has my least variability? Well, it is this all good. And notice also my all good has this smallest variability range. So that means all good is going to be my best mean indicator for a typical value. So our lesson summary is this. We can compare distributions based on their means, but variability must also be considered. The mean of a distribution with a small variability is to be considered a better indicator of a typical value than the mean of a distribution with a greater variability. So means are really only good indicators if I'm working with a small variability size. Okay, here's your exit ticket. Consider the following statement. 2 sets of data with the same mean will also have the same variability. Do you agree or disagree? And explain. Then your second questions are using these 2 dot plots up here. Compute the mean number of goals for each distribution. And then for which distribution, if either, would the mean be considered a better indicator of a typical value? Explain your answer. When you are done, go on to Dreambox until the end of the day. Alright, good job today, guys.